Hello, my name is Diego Manuel Delgado, and I'll be talking about the research I conducted under the Robotics Institute Summer Scholars Program at Carnegie Mellon University. My research focuses on healthcare robotics and more specifically utilizing simulation to train robots to perform varying caregiving tasks. The official title of my project is Sim2real Transfer for Capacitive Sensors Utilizing Assistive GIM's Capacitive Sensing Simulation Framework. Now, to add a little bit of context for the motivation behind this research, due to the inherently tedious nature that caretakers experience while aiding with activities of daily living, or ADLs, there is a lack of adequate assistance for those in need. Robotic assistance, on the other hand, presents an alternative method for providing help to those who require support conducting everyday tasks. However, the state of robotics isn't quite there yet for wide use due to the unsafe nature of human-robot interaction. Technology is being used to ease robot-human interaction. An example of technology such as this is the use of capacitive sensors. Capacitive sensors can measure the change in capacitance on conductive surfaces, and based on this, one can predict the distance from that conductive surface and the sensor. This provides near-range sensing as well as the unique feature that the sensors can sense through non-conductive occlusions such as cloth or clothing. However, when it comes to research with capacitive sensors, it is very slow, costly, and unsafe. To overcome this, we propose the use of simulation to train robotic caregiving controllers with simulated data which can later be transferred into the real world, thus providing a cheaper, safer, and more instructive alternative to real-world experimentation. For simulation, we utilize Assistive GIM, an open-source physics simulation framework for assisted robotics, which includes a novel capacitive sensing framework. The timeline of the project is presented as follows. First, we designed and 3D printed a tool with the purpose of performing a cleaning task along a person's arm. Moreover, the tool looked to accommodate a mounted capacitive sensor created with the use of a Teensy 3.2 development board and copper foil tape. We ended up with a capacitive sensor containing a 3x2 grid with 6 electrodes. Secondly, data collection was carried out by utilizing a Stretch RE1 robot with a dexterous, as this allows us great range of motion in 6 planes. By moving the sensor in a predetermined trajectory, we captured the changes in capacitance as the sensors approach the arm, which in turn allows us to map the changes in capacitance in the distance from the sensors to the closest point on the arm. Lastly, the same trajectories were replicated in simulation where we performed system identification in order to create a faithful simulation environment. Here we look to compare the data we collect in simulation to our real-world data and then perform optimization on the parameters to bridge the gap between the simulation and the real world. For results here, we can see a plot of the changes in capacitance for the first trajectory conducted, which was a simple straight movement across a person's arm with the capacitive sensor. Here we see the expected behavior as the spikes in capacitance are experienced by electrode 1 to 3 and is later followed by electrodes 4 to 6. This behavior is seen due to the fact that electrodes 1 to 3 pass by the arm first, thus causing a peak in capacitance readings, thus concluding that our sensor design is working correctly. With this, we presented the foundation and initial findings for performing Sim2real transfer of capacitive sensors utilizing Assistive GIM's capacitive sensing simulation framework. Now for future work, we look to optimize simulation parameters utilizing covariance matrix adaptation evolution strategy, or CMAES, with the purpose of creating a simulation environment with higher fidelity. Moreover, we look to complete the Sim2real transfer after this optimization. With this, we will later train a post-estimation model, and lastly, we will look to train a robot controller in simulation to perform evading tasks along a human limb, which can later be transferred into the real world and see how the robot performs this task. Now, I would like to take a moment and extend a sincere thank you to Dr. Zachary Erickson and Yufei Wang for allowing me to work under their mentorship through this summer, as well as for all the help and unconditional support that they provided through the whole project. A big thank you to Rachel Bershin and John Dolan for organizing RIS and being present through the whole process. Finally, a big thank you to the CMU Robotics Institute for funding this research. Thank you for your time.